Electron configuration is how we put electrons into the different distributions around the atom. And we talk about electron configuration for an atom, we talk about ground state electron configurations. As soon as you zap electrons with energy, they can go anywhere. So electron configuration of an atom tells us how the electrons are distributed amongst the various orbitals. So what was discovered in the 1920s is that you could split the signal on a spectrum for an atom. And splitting the signal signified to scientists that there must be two electrons at a particular frequency. All right. So the fact that the two electrons could exist at a particular position said that you needed a fourth quantum number, a number that differentiated the two electrons, right? So one gets a plus a half designation, the other gets a negative half designation to differentiate between the two electrons in a particular space, at a particular orbital. So this leads to what's called the Pauli exclusion principle, which says that, yeah, you can have two electrons in a space as long as they're spinning in opposite directions. So no two electrons can have the same atom can have exactly the identical quantum numbers. So a maximum of two electrons per orbital with opposite spin. All right, so rules for putting electrons into these distributions. First rule is the electrons want to be as close to the nucleus as possible. So when you're making a ground state electron configuration, the Aufbau principle, you put the electrons in at the lowest energies first. Two, a maximum of two electrons, right? The Pauli exclusion principle. So in these distributions or these orbitals, you can put a maximum of two electrons. So with the first energy level, principal quantum number 1, we only have one shape, right? The 1s orbital. So that one shape is one space where the electrons can go. If I'm putting an electron into the 1s for a hydrogen atom, right, at ground state electron configuration, by convention, the electron is spinning in a direction, so we put an arrow to indicate the electron, and the first one in an orbital is always pointed up. So this would be the ground state electron configuration for hydrogen. Well, in that first energy level, in that 1s shape, there's enough room for two electrons, according to the Pauli exclusion principle. So that second electron can go in that space. That gives us helium's electron configuration, but it has to be spinning in the opposite direction. So you put the next electron in with the arrow pointing down to indicate opposite spin. All right, a shorthand way of showing this is to put the principal quantum number, the shape, S shape, and the superscript to indicate how many electrons are in that shape. So as many as two electrons can go in the 1s orbital, and then the first energy level is filled. That's the only orbital that exists in the first energy level. Then we go to the second energy level, where we have introduce a new shape, the P shape. There's three orientations for a P, an X, a Y, a Z, so there's 4 places to put electrons in the second energy level. So if you're doing the electron configuration for lithium, right, the 1s is filled. That next electron has to go up to the 2s. All right, paramagnetism and diamagnetism are important for how they determined electron configuration. So the way it works is if you're a diamagnetic element, when you're put through a magnetic field, you're unaffected by the magnetic field. If you're a paramagnetic substance, you're shifted towards one side of the field. So that means you have an unpaired electron. So if you have paired electrons, you're unaffected by the field. If you're an unpaired electron, you're affected by the field. So some smart student would look at this and say, oh, okay, so if I have an odd number of electrons, I would be paramagnetic always, and if I was an even number, I'd always be paired, and I'd be unaffected. I'd be diamagnetic. Well, that's true for paramagnetic in terms of odd numbers of electrons, but when you get to diamagnetic, you have to be careful with being even. You have to look at the electron configuration. So starting the second period, right, the second energy level, we have 4 places to put electrons. Each of them can take 2. So lithium, you put 1 electron in the 2s. When you get to beryllium, you fill the 2s. And because we're talking a multi-electron system, the 2p, because of its shape, right, having a less penetrating shape, that dumbbell shape, it's a higher potential energy. So the 2s fills before the 2p. So once the 2s is filled, then you start putting electrons in the 2p. So if I'm looking at lithium, whether it's diamagnetic or paramagnetic, it's going to be paramagnetic because it has an unpaired electron. Beryllium's ground state configuration would be diamagnetic because they're all paired. If we're looking at boron, it's odd number of electrons, so it would have an unpaired electron and therefore be affected by the magnetic field. So the question was with carbon. Well, would carbon be diamagnetic or paramagnetic? Well, carbon is always paramagnetic. What this means is electrons will singly occupy orbitals before they doubly occupy orbitals. And this is your last rule that you use for assigning electrons to spaces. When two or more orbitals are of equal energy, each one is singly occupied before it's doubly occupied. The most stable arrangement of the electrons is one where we have the greatest number of parallel spins. So when we go to nitrogen's electron configuration, we'll have one electron in the X orientation for the P, one electron in the Y orientation for the P, and one electron in the Z orientation for the P. They're degenerate, they're the same energy, so because of electron-electron repulsion, the electrons would rather be away from each other than double up in a space. You run out of room for being singly occupied when you get to oxygen, so you got to start doubling up in one of those two P's in order to conform to the Aufbau principle. Fluorine, you double up, and then when you get to neon, all of the two P's are filled, so nitrogen is paramagnetic, oxygen is paramagnetic, fluorine is paramagnetic, only neon is diamagnetic here. So the second period is finished. If you want to put another electron in, right, do the electron configuration for sodium, you've got to start putting electrons into the third energy level. All right, so when you start the third energy level, the third period, you're starting off with 10 inner electrons. All right, so you've got the 1s filled, you got the first energy level filled and the second energy level filled. So you have 10 core electrons. So 10 inner electrons blocking electrons going into that third energy level. All right, so this is what the brackets around neon represent. You're starting off with a neon configuration and you're adding on to this. All right, so this is going to have a lot to do with why sodium behaves the way it does. We have 10 core electrons shielding that outer electron from feeling the nucleus, right? So 10 blocking electrons. So we put one electron in the 3s, and we get to magnesium. We fill the 3s, and then when we get to aluminum, silicon, phosphorus, going across the third period, we go all the way over to argon, and we have filled the 3s and the 3p. So the question comes: you want to put another electron in. You want to write the electron configuration for sodium. Does that electron go into the D shape, right? When you go into the third energy level, you introduce a new shape, the S shape, the P shape, and now the D shape with its 5 orientations. Fact of the matter is, even though the 3D is closer to the nucleus than the 4S, because of that cloverleaf shape, that non-penetrating shape, it's actually higher potential energy than putting an electron further out into the 4s. So the 3D, because of its shape, is a higher potential energy than the 4s. So when you get to sodium, starting the fourth period, you put that next electron into the 4s. You've got an argon core, and that's 18 inner electrons, and you're adding that 19th electron out in the 4s. So calcium, you now fill the 4s, and when you get to scandium, now you start putting electrons back down into 3D. So 3D1. So this is the transition metals. This has a lot to do with how they behave, right? I mean, potassium only loses one electron because you've got these core electron shielding that outer electron from feeling the nucleus. Easy to take off. Calcium can lose 2 electrons. Well, when you get to the transition metals, because of this weird overlap, we have these multiple oxidation states, right? These weird, we can't determine how many electrons they're going to lose. And it has to do with the fact that the 4s is now overlapped with the 3d. So, first transition series, right? You have a incompletely filled d subshell. All right, so you're putting electrons into the d at this point. That's the definition of a transition metal. So 1 electron goes into the 3d, 2 electrons go into the 3d. We get to vanadium, 3 electrons go to the 3d, and we're going merrily along here. And then you get to chromium, 4s2, 3d4. Well, no, it's 4s1, 3d5. So what's the rationale behind this? Well, the rationale is, as you get more and more protons in the nucleus, that 3d gets pulled closer and closer energetically to that 4s. So all of a sudden, it's all about Hund's rule. The fact that the 4s is now basically the same energy as the 3d. Electrons would rather be singly occupied than doubly occupied, and that's your rationale as to why we have this anomaly. All right, you expect this, right? 4s2, 3d4. You get this, 4s1, 3d5. So Hund's rule is the rationale as to why we have all singly occupied orbitals. So then we go back, we put an electron into the 4s, right? 4s2, 3d5, 3d6, 3d7, 3d8, 3d9. No, we have 4s1, 3d10. And the rationalization for this is now finally, because you've gotten 21, 22, 23, 24, 25, 26, 27, 28, 29 protons pulling on that 4th energy level. It is now pulled, the 3d is now pulled back below the 4s. So the 3d is back where it belongs, right? Lower in potential energy than the 4s. It's closer in. So energetically, better to put electrons into the 3d now than the 4s. And we finish off with zinc. We have now completed the 3D, and after the 3D, now we have to go back and start filling the 4P. All right, so 4P will fill after the 3D. So now we have a krypton core. We start the 5th period with a krypton core. We fill the 5s and then the 4d exactly the way that we filled the 3d, and then we go across to the 5p, and that's the 5th period. The 6th period starts with the xenon core. Now you might have asked yourself, all right, so when we get to the 4th energy level, we've introduced a 4th shape. We have an S shape, a P shape, a D shape, and an F shape. Well, where do we start filling the Fs? Well, after the 6s fills, then we start filling the 4f. So the 4f fills after the 6s. Again, this overlap, right? Because of its shape, this non-penetrating F shape, even though it's closer in, the 6s, because of that sphere shape, is lower in potential energy than the 4f. It's called the lanthanide series. So 7 orientations for an F, 2 electrons apiece. So those 14 elements that are pulled out of the periodic table are the lanthanides, right? You're filling the 4f with the lanthanides. And then you go back and you start putting electrons into the 5d. 7th period, radon core, the 7s fills before the 5f. And then after the 5f fills, you go back and you start putting electrons into the 6d. And that's how you put the electrons in the orbitals. So if we were to shove the F into the periodic table, it would shift everything over and, kind of destroy the whole predicting periodic properties thing, right? Chemical reactivity and physical properties. But this is how it would fill. All right, so if I was looking at this right after the 5p is filled, I go down to the 6s, then I start putting electrons into the 4f, and then the 5d, and then the 6p. So this is how the periodic table is laid out, right? The S's fill over on the left side, the D's fill in the middle, the P's fill over on the right-hand side, and the F's are pulled out on the bottom. This is how it fills. This is your map. So if you're ever lost, just look at where you are in terms of what the electron configuration would be.